Thank you, Olivier. So thank you very much for the opportunity to speak. Olivier, I have a bunch of different talks that I give at chapter meetings and elsewhere. So I can talk about AI, virtual clinical trials, or digital twins. Olivier said, yes. So this is a slightly different combination and will be a little bit truncated as a result. Also, it's a play in multiple acts. So I won't actually get here for a few minutes. Okay, so first of all, I wanted to thank you for the opportunity to come here. You can see I rented a mid-sized pickup, so they gave me a 2500 Bighorn. I admit it's not a dually, so Eric qualifies, I guess. The other interesting experiment is I tried going from 30 feet above sea level to 14,000 feet above sea level in one day. It worked more or less. You can tell my sinuses are bothering me a bit today. But thank you for the opportunity. I do have some disclosures that doesn't really relate exactly to what I'm going to talk about today, but there will be some off-label uses discussed. Very briefly, a little background with myself. I'm Canadian. I moved to the United States in 1993. My background's in engineering physics. So I took engineering science at the University of Toronto, and then I went into the medical biophysics program there. Initially as a computer support person. We had in the VAX 11780, if any of you remember back to those days, that was roughly a laptop that served 50 people through multitasking. And I was tasked with creating a digital mammography system. There weren't digital mammography systems in 1987. The system evolved over time. The work was done at Princess Margaret Hospital, which I think a lot of you will know. That's sort of the Sloan Kettering of Canada. And with time, I learned medical physics, a lot of it from this guy, who's Jack Cunningham of Johns and Cunningham fame. I will not tell you that I learned a lot during classes from him. A lot of the classes went like, how did I do that derivation? Oh, I remember. I was at the Paris ICRU meeting. Oh, and then we had 40 minutes about the food in Paris. But we did learn physics eventually. And eventually this system became commercialized by a company called Fisher Imaging, which was actually in Denver in the 90s. And I spent a lot of time there. And that's the first digital mammogram. And that system went into clinical trials at Thomas Jefferson University. And at that time, John Boone, who you might know, had just left as the medical physicist there. So he helped me get that job at Jefferson. And I was able to follow my baby into the States. And I planned to live here for 3 years. It's now 33 years, but oh well. In 2003, I was recruited to head the medical physics program at the University of Pennsylvania. And I'm predominantly do research today still, and I still develop medical imaging systems, mainly for breast imaging. But of late, about half my time's been spent doing AAPM things. So I wanted to just briefly tell you where we are in the AAPM in 2026. So it's useful to look back a little bit. The AAPM's been around since the early 50s. The Rocky Mountain chapter was created in 1970. So you've been around for a long time too. And the AAPM has changed a lot in those 75 or 70 years or so. Going from 50 people in the first meeting in 1958 to almost 10,000 people today. The AAPM is run through the board of directors that has the ultimate oversight of the organization. There are 38 voting appointees and either 12 or 13, depending on the time, if you're non-voting appointees. The voting appointees include representatives from each of the 21 chapters, as well as 12 ad hoc members. Also, the ex-com is on the voting part of the board, and that is Imran, your current your current representative on the board. The non-voting members are predominantly from the councils. The current ex-com consists of Sam Armato from Chicago, who is our treasurer, Sonia Dietrich from University of California, who is the secretary, Mahesh requires no introduction. He's the current board chair. He was president last year. Robin Miller from up in the Seattle area is the current president, and I am the president-elect. I'll become president in January. Our executive director is now David Gamble. He's been in the job about 2.5 years. Before that, it was
Angela Kaiser.
Thank you. I couldn't find that neuron. All the work of the APM is done through the councils. So the councils report to the board, and they're divided, as you can see, into science, professional, ed council, admin, and most recently, international council. Within each council are many working groups and task groups and committees and subcommittees. And so one of the things I want to point out, part of this is how to navigate the APM, because it is huge. If you go to the directory tree of the committees, the committee directory tree, each committee element in the committee tree has a reference to the org chart. And if you click on that, it will show you sort of all the committees and subcommittees and task groups and so forth that relate back up to that council in this instance. And this is the best way to sort of navigate and to try to find things that, you said, oh, why are we working in, vaginal brachytherapy or cervical brachytherapy? It'll turn out that, yeah, actually there is probably something going on in cervical brachytherapy. All the meetings for the AAPM are open. And this I really want to stress, especially for the young people in the audience. All of them, virtually all of them are open. There's very few. There's a few where we go into executive committee when we're talking about like salaries of staff or things like that. But the vast majority, 99.99 something % of these meetings are open. Use that QR code and pull up the directory structure. For example, I can tell you Imran has a meeting at, all the times are Eastern for me, at 11 o'clock on Monday for the regional organizing committee meeting. You guys are welcome to join that as well. And the cool thing is once you start joining these things, you'll start to understand what you're interested in and how you can participate in the APM more. Okay, the APM is organized into rules, bylaws, and the articles of incorporation. So why would I mention this today? We are currently in the process of revising these, a very major revision. And I should go back for a second. The reason we're revising it is by who has to approve these changes. The further down on the screen, the more rigorous the approval process is. And what we want to sort of move away from is having the membership do lots of sort of fiddly little things. The actual rules of incorporation and everything are in what I like to use as the compendium document that I've highlighted in red and that QR code there. This is where you can find out, like, well, what does the treasurer do? What does the the president-elect do? I mean, I had to read this like every 3 weeks in the first 6 months of my tenure. Why do we have a members committee and what is their role? Things like that. Within the actual committee tree, there are more hints to this. There's a section on most committee pages that says bylaws. If you click on it, it'll take you to where in the bylaw it was created and what the rules are for that committee. And then there are also separately a set of rules, and you can click on that, and then you'll find more about, like, for example, in this case, the executive committee provides oversight. And basically, we provide oversight and run the organization between board meetings. We ultimately report to the board. The actual governance rules have changed, and they change continuously. These are the changes since 2017. And yeah, it's a little bit small print. I don't actually expect you to read them, but there are ongoing changes. What we're proposing to do this year is a much larger modernization. A lot of the rules date back to when we started, especially the rules of incorporation, to when we started the organization 70 years ago. So for example, all meetings need to be in person. All tallies have to be on paper. There are rules like that written in. And these are not tenable today when we have 10,000 members and not 50 members. So also, like the DC, the laws in the District of Columbia have changed substantially over the years. So GovC and rules committees have, the government committee and the rules committee have basically gone through and done this Herculean task of looking at every single rule, every single bylaw, and every single article of incorporation. And they've recommended changes. And so here are sort of the top 10 facts of the changes. So first of all, the structure of the board and the dues are not changing. So those are sort of the hot sort of flashpoints in a lot of prior discussions. So there's no change to like the construction of the board or to dues. This is not it. What's happening instead is we're changing the sort of where things sit. So that, like, for example, if we want to create a new committee, we have to get membership and board permission, right? So, these things don't make sense anymore. And so we're moving them as sort of high up in the chain with the least oversight as possible for making changes. So the governance document is going to be a little bit longer. There is some flexibility in the rules to allow us to add things in. We're changing the term of the secretary so that the secretary can be reelected once. Currently, the secretary is a 3-year position. And it was felt that for stability, it would make sense that they have the same sort of rights as the treasurer has. There are going to be reasons to remove elected directors. So we can actually petition. There's very specific reasons like malfeasance, things like that. There's a provision now that members can actually petition to call a meeting of the board. The number of board meetings is changing. The threshold for creating a bylaw amendment is changing. 5 people made sense when there were 50. We've gone very conservative and we only require 25 people to make a bylaw adjustment. For organizations the size of the APM, a lot of them have 200 to 1,000 members to make a bylaw adjustment. And as I said, we're just reorganizing things. So why am I telling you this? Because you're going to be voting on it soon. We had presentations to the board in the early part of the year. The board approved these changes at the April board meeting. This began a series of membership education communication efforts. I'm hoping you've seen them. This will be discussed extensively at the town hall, the annual business meeting in town hall, which is, I made the adjustment for time zone. It is 1:30 in the afternoon on July 9th. Any full member of the AAPM can attend. And you have the opportunity to raise questions. There will be material sent in advance, and you can send questions in advance. Then after the annual meeting, we will have a vote. And so you'll be seeing a vote. We're going to be asking your permission to make these changes. I think they're very sensible changes. I don't think they're very controversial. But I've sort of learned in the APM there's nothing that's not controversial to some people. So we'll see how that goes. The next thing I'd like to talk about briefly is where the APM is, or what the APM is focusing on. Excuse me, I am used to a much lower altitude. So we have a strategic plan that goes through the end of 2027. This was decided in 2024. And a lot of these things are sort of obvious. In 2027, we'll create the next strategic plan. One of the things that was brought about was operational stability. So the APM gets revenue from a variety of sources. We get revenue from the journals, we get revenue from the annual meeting, less so from the spring clinical meeting and the summer school. We get revenue from dues, for example, the jobs board. As society has changed and as we have to go to more sort of online solutions, so for example, we now use a different provider for the job board, which is a professional organization who's got like a legal structure to allow them to sort of offer jobs to people and such. These have all cost us money. And so from having a profit in 2022 to the current day, we are now operating in a deficit. So last year, the organization lost about $1.5 million. That's not terrible in some sense because we have money. So I'll show you in a minute. We have reserves. This is not existential, but it's not what we want either. Sam Armato, the treasurer, and the finance committee went through the budget line by line, and it's an enormous budget. And they identified about $800,000 they could save. That included cutting, for example, all council in-person travel this year. The plan for next year is to cut it another $800,000, and that should get us back to being operating basically at a neutral budget. But we're working on that. Oh, actually, so here you go. Here's the information I just sort of outlined. So we get about $12 million in revenue. We had about the projected shortfall for 2025 was 1.1, ended up being 1.6. And the projected deficit this year is 0.7. Our total assets are about 32 million, and of that in cash or in investments is about 17 million that we can readily take and use. Not in that, you can see there was sort of a difference between 17 million and 32 million. A big part of that is the E&R fund. So the E&R fund has a balance in excess of $5 million today. Today, all scholarships, all grants, all awards are being paid directly from this fund. To achieve that, a couple of years ago, we moved $2 million from reserves into the E&R fund specifically. But anticipate in the future getting more frequent emails about contributing to the E&R fund. Everyone on XCOM has donated. Everyone on the board of directors is asked to donate. If you think about what the APM has done for you, hopefully you see enough value that you'll be willing to give back in some way. One of the things that came up in the session just before the break was the relationship between medical physicists and the government. This is changing. When I was recruited to this position, I was told it would take 20% effort this year. And as you notice in my graph, I said 50. One of the things is that we are responding to actions of the federal government essentially on a weekly basis. There are changes to, the linear no threshold consideration for the basis of dosimetry. There are changes to sighting and shielding and environmental considerations so that small pocket radiation nuclear power plants can be built. So there's an effort right now to put something like 500 small nuclear power plants across the country. These are the size of a shipping container in terms of the infrastructure, but the idea is you'll site them next to data centers. And the way to achieve that goal is basically to eviscerate the rules on how to site nuclear power plants. I could go on and on and on. It's a weekly thing. It's just, it's this one now. It's like whack-a-mole. Or I guess out here, what is it? Not a varmint. Marmot. A marmot. Whack-a-marmot. They just keep showing up, right? So for the first time in over 30 years, last year we had an advocacy day. And I know some of you went to that because Colorado was represented. We had over 100 meetings in the Senate and the House. And we championed two things that year. One was ROCKR, which is a initiative of the radiation oncologists to change the funding structure so that it's funded basically by patient rather than by treatment. There are incentives right now to continue doing 30 treatments on a patient when hypofractionation would allow you to do something very different. The other thing that we helped back at that point was the Veteran Affairs Act. Right now, because of the way salaries are set up for people in the Veterans Affairs Administration, no medical physicists would take that job. So they're all funded through consultancies. And it would be much more cost effective. I think the number was the government would save like $50 million over 10 years. And it would be much more stable, and it would achieve a more uniform level of care across the VA system if we could have medical physicists in the VA. All of this is organized through something called GRAC, the Government Relation and Affairs Committee. Anyone on GRAC here? I think Imran, you said you attend some of the meetings, and again, I would encourage you guys to attend them. They work at the intersection of medical physics, policy, and regulation, which is exactly what we were talking about a few minutes ago. We need to have medical physicists involved at a higher level than we have in the past. We sort of relied upon Astro and ACR and RSNA to have our best interests at heart. And what we've come to learn is they do, but we might have better interests. So we need to be there. We need to be in the scheme of things. You know, for example, I know at Penn, if I can't justify something through a federal regulation or through the joint commissions or something, my administration tends not to want to pay for it, right? So like dual energy CT or cone beam CT on C-arms, we tend to do very little with that because it's not regulated. There are clear standards. You know, the AAPM has guidelines on these things, but my administration sort of says, well, that's not in legislation, so we're not paying for it. And so it diminishes our ability to do what we think is appropriate. Within CHAMPS, and this got mentioned as well, or within GRAC is CHAMPS. CHAMPS is the state champion program. And the idea is what GRAC does internationally, CHAMPS does domestically within the state. So this is, somebody, and there is somebody in Colorado, it might be in this room. Who's in CHAMPS in this room? Is anyone in CHAMPS in this room? Okay, so there are at least 3 people. So somebody is working with your legislators and getting advance warning of changes, hopefully. You're discussing it, you're looking at the implications, you're coming back to the national organization and getting advice. For example, in Arizona, where I spoke a couple months ago, there was a company that was pushing these things called a Nest, which is like a ceiling mounted radiation protection system for interventional radiologists. And they were trying to make it so that it was mandatory. We had to fight that. So we want to strengthen partnerships. We want to expand engagement. Advocacy is most effective when it reflects the voices of the entire community. And that means everyone in this room. There's the old joke about, like, how do you know an extrovert engineer? He'll talk to your shoes when he's talking to you. Same is true of medical physicists, right? We are not extroverted people by and large. And we have to sort of fight that natural reticence to want to speak about our profession. What on here? Okay, there we go. Why does this matter to you? Because it's going to affect the way you practice medical physics. It's going to affect our ability to staff places, and we have to be proactive as a result. If we're not at the table, then decisions are made without us. And so that brings me to my AI-made slide and Rebecca's. Some of you might recognize Robin, and I have her permission to use the slide. We need you to be involved. Become a state champion. Take action through the APM Advocacy Action Center. Did you know we had one? How many people knew we had one? Yeah, we do. And join GRAC, join Econ, or join the subcommittees thereof. Okay. I talked about the strategic plan. And part of the strategic plan was to sort of look for new avenues where medical physicists have a role. It's quite clear that the way medical physics is practicing is changing. You just have to look at the advent of AI, and I'm going to talk about that in a few minutes to realize that. So in 2023, Jim Dobbins commissioned a report called the Ad Hoc Report on New Science. And in it, and I encourage, it's on the website, I would encourage you to look at it. In it, they identified new avenues for research and for clinical involvement of medical physicists. Sort of completely new things that medical physicists maybe have never thought about before, including AI, virtual clinical trials, and digital twins, all the things we're going to talk about today, and other things. And the basic idea was, what would medical physicists look like in 30 years or 25 years? And so we called the summit for a number of reasons. We wanted to stress test the ideas of the report. We wanted to solicit any new ideas that occurred or risen in the last 3 years. We wanted to identify priorities and also to get buy-in, especially from our peer societies. So there were very few AAPM members at that meeting. It was mainly our peer society members from the peer society and executives from the peer societies. So the 3 priorities we chose to focus on for the summit were AI, theragnostics, and what's called frontiers of science. So these things like digital twins and virtual clinical trials. These are things that are really at the edge of what we're doing today. The group, the fellow from MIM that spoke, talked about having software to do dosimetry in theragnostics, right? And he's talked about Fluidica and stuff like that they could use that with. There's a problem, though, that the FDA has not approved us to do those things, Fluidica. It's approved for 200 millicuries in 6 treatments, period. So we would have to sort of work outside the sort of realm of the advice or the approved use in order to do these things. It's different in Europe. They have much greater purview in how they can use these. And I presume that part of the MIM software is more popular in Europe right now. But medical physicists need to have a role. We need to be doing doses. We need to be calculating the dosage of critical organs. We need to think about different stopping criteria than simply administering the full 200 millicurie. We need to think about how to do boost therapy and things like that if we don't think that the therapy is going to have a viable treatment dose. And then we talked about other things that came up. We asked people to concentrate on things like workforce, science, and industry when they were thinking about this. And what we did is we asked people to envision what was their day like 25 years in advance. And how many people recognize this cartoon from the late 1960s? All right. George Jetson. Would you believe that he's living in our day? I think George Jetson was set in 2025. So we had 2 unique responses. So first of all, think about if I asked you that question in 2000. If I asked you that question in 2000, you would have said, I would be doing the same things I'm doing today. We'll have better Linux, we'll have better CT scanners. We might have a new modality that I might have to deal with. I'll have better QC equipment than I did, in 2000. That is not the answer you're going to get today if you ask someone, right? They're going to look at AI and stuff and say, I don't even know if I'm going to have a job, right? And when we ask people, their answers went in one of 2 ways. One thing was common to all of them. They all agreed we'd come in and start with a cup of coffee. So coffee will not change in the next 25 years. So that's good for you that are addicted to caffeine. I am completely decaf, I'll just say. After that, there were 2 sort of polar opposite answers. One was, this will be the land of milk and honey. I will be practicing the medicine the way I was taught to practice medicine. I will have time to talk to my patients. I will be loving it. I will be doing medicine the way I think medicine should be done. Because all the mundane stuff, all the routine stuff will be done for me. The other side was AI is going to do all the easy work, and I am just going to be slammed. I am going to be burnt out in 3 years. I'm only going to have the toughest cases. I'm only going to be looking at the worst treatment plans. I'm only going to be talking about the patient that has 3 implants and needs to have an MRI. The answer is clearly somewhere in the middle. Right? I mean, it clearly is, but we don't know what that's going to look like. What came out of this the conference summit was 3 new foci: innovations in regulatory science, in educational innovations, and ethics and trust, which was a very interesting thing. And I'm going to touch about it in a couple slides from now. People do not trust scientists today. There is an overwhelming public message that is going out that scientists are working for their own best interest. I do breast cancer research because I want to keep getting royalties from breast cancer companies. I know the answer to how to stop breast cancer, but I'm holding it back because I'm a bit of a bastard. Sorry, it's being recorded, isn't it? But I've been told that to my face, right? There are people that really believe this. And that lack of trust is a problem. Now, the interesting thing is who do people trust most? You want to guess? In our profession, who do people trust most? Nurses, yes. Why? Because they see them every day and they express empathy to their condition every day. We don't see patients every day, right? You talked about this one. We need to set ourselves up so that we're not linked to how many machines we test, but how many patients get imaged and how many patients get treated. So that introduces me to the main topic for this lecture, which is AI and medical imaging, virtual clinical trials, and digital twins. So a few years ago, Jeff Hinton, who won the Nobel Prize in physics, I think 2 years ago now, he said that radiologists were going to be like the coyote going over the cliff, geographically appropriate, I understand, and that he just hasn't looked down yet and realized he's standing on air. 10 years later, just in January, Elon Musk said, stop sending people to medical schools. It's pointless. AI and robots will do it all and better. I don't believe those. I believe this guy, Kurt Langlois, who's at Stanford. Radiologists who use AI are going to replace radiologists who don't. And by corollary, medical physicists who use AI will replace medical physicists who don't. We've had lots of opportunities to bring other science into our field. And I won't enumerate them, but you probably know through the history of the organization, we've not always been so receptive to new ideas. I started on AI task groups before it was called AI in the early 2000s, when breast CAD was becoming prevalent. And we argued in the early 2000s that medical physicists needed to be involved in breast CAD. And we were uniformly told that is not what physicists do. That's what computer scientists do. Advance 20 years, and we have a very different situation. And the interesting thing is, as somebody pointed out, I think Brad pointed out, we're one of only 2 non-MD groups that are board certified. And we're board certified to do quality assurance and safety, right? This is what AI needs today. Why is this imperative? This is a study from December. The role of doctors is changing forever. Patients don't trust us. Others say they don't need us. We have to rethink ourselves, and we have to reinvent ourselves back to what we originally were, healers. Do we have documentation of this? Yes, this is from ChatGPT alone. 40 million people use ChatGPT on a given day to get health advice. 1/4 of ChatGPT users routinely seek health advice at least once a month from ChatGPT. And they're sure that the same is true of Claude and Gemini and Grok and what have you. They check symptoms. They want to understand medical terms or instructions. They want to learn treatment options. And in 7 of 10 health conversations in the last year, 7 of 10 of these conversations take place outside of clinical hours. And 68% of these people go to their doctor and say, Claude said, or ChatGPT said, I have this, right? And then the doctor has to say, well, no, actually you don't. You have this other thing. And then you have to convince them that Claude was wrong. I'll give you an anecdotal story that is true. I had a friend. So one of the things I was going to tell you is the last time I actually visited this area, I was at Philmont with my Boy Scout troop. And one of the other fathers on that trip is no longer with us. He had pains that he woke up to in the middle of the night. He walked downstairs and he Googled symptoms of a heart attack. And he was found by his wife the next morning, dead at his computer. All right? This is what we want to avoid. We think we're more productive. This is a study from McKinsey Healthcare Conference earlier last year. Right? 60% of people think healthcare costs are too much. There's all these problems that people have. But if you look at productivity, calculated, God knows how. So I'm not supporting this too much. I treat consultants like I treat Claude. But they basically claim that there's been little to no productivity gain in healthcare in the last 25 years. And we can think about that. The question became, are we doing unnecessary things efficiently, right? And I think a lot of people answer that the answer is yes, right? So we have made things more efficient, but we've not necessarily made things better. So these trends are not sustainable. Imagine just in terms of the electronic health record and how it's done today. There is an intrinsic tension between how patients use the electronic health record, and they have full access to it today, and how providers use the electronic health record, right? The way you access the data has to be different. The way you explain things have to be different. What we're doing at Penn is we've put LLM in the center of this. And so this is work that we're doing at Penn. We basically have an agentic AI system with apps and agents that query the EHR through an LLM. And what this allows you to do is adapt and instruct, how the LLM will treat physicians and patients differently, right? So that you can say things like, this needs to be explained at an 8th grade level, right? You need to be able to explain these tests in this way or that way. You need to do comparisons over time, so forth. What we're realizing is that's not enough. We've actually working with Epic to add a data layer in front of the EHR, and they are resisting. But that data layer has to bring in other parts of the medical record, other things that are not stored in the EHR. And the reason for this is there are semantic rules in how you access these data, and you need this layer in order to sort of interpret these rules. The other thing that we're going to be adding is an orchestration layer. So agentic AI is basically AI that is targeted to very specific questions. And we have lots of these agents today in the hospital. The orchestration layer will help us choose which is the most appropriate agent for these tasks. So how will AI affect routine medical physics? Ask yourself a very simple question. What do I do today? Right? Essentially, everything you do except rolling the water tank into the LINAC room can be done with AI, right? And somebody's going to robotize, make someone in this room on the side or the back here is going to have a robotic tank that will walk into the room at some point and set itself up and plug into the LINAC. Don't know about spilling water. So how can AI help you? Ask yourself, how can AI help you? Auto contouring and auto treatment planning is becoming more common. Lawrence Court and I'm blanking on his name too. He works with me. The equivalent at Penn, his name will come to me in a second. Okay, it's a good Shakespearean name too. Rafe Macbeth. Thank you. For the patients. They are pushing this through. We have significant efforts. There's a thing called Hypo Africa. How many people are familiar with the Hypo Africa effort? So they're having, okay, the meeting was over. The meeting was probably about 2 hours ago now. Every Saturday at 11 a.m. Eastern, there is a meeting called Hypo Africa. And it's how do we bring radiation oncology to Africa? Where you have countries that only have like 3 CT scanners and no LINACs. So what do you do? Well, how do you get a LINAC into a country like that? That's just money. We can do that. But how do you then staff it and such? AI provides some of that answer. And it's called Hypo Africa because most of what is done in radiation oncology in Africa today is palliative. Chart checks, monitoring system performance. For a diagnostic physicist, that CT dose tracking software we have to look at, and 90% are fat patient, right? And a few are arms in field of view, and there's a few, 1 in 200 or something might be a legitimate concern. What else can AI do? Image processing and reconstruction, image interpretation and reporting, predicting failure modes, teaching, most likely, conducting research. If you look at the math field, AI systems have solved a significant number of Erdos problems in the last 3 years. They have done novel mathematical research, linking fields in math that no one thought were obviously linked to solve Erdos problems. So, what are the challenges of AI? Does this patient have MS? What about now? Do they have MS now? There's clearly something in the spinal cord that you can see. There's clearly a lesion in the spinal cord that you can see now. The top image was acquired in an AI-based reconstruction to save time. Right? This acquired the data in 1/3 the time of a normal acquisition. Right? Exactly what we talked about today. The risk of losing information. The bottom image was a conventional reconstruction. The advantage here was this patient was an ongoing patient with existing MS. And we're quite certain the MR scanner did not cure them. Right? And so we went back and we imaged them again. But what if that patient had come in with de novo disease? What if that patient was coming in for their first diagnosis of MS? We could have delayed their diagnosis by years by using this algorithm. Why? Because it's outside the framework with which it was trained. The manufacturer did not provide it with enough MS patients to train the algorithm. So what are the challenges of adopting AI in medicine? It will not be that AI makes mistakes. AI will always make mistakes, just as we always make mistakes. The problem is if we fail to provide adequate and proper oversight. So you as medical physicists, and this is my national organization beating up the local people, you're going to need to learn AI model literacy. You're going to need to learn how to practice clinical judgment when using AI. You're going to have to provide accountability and governance for AI because we are board qualified to do that. Right? We've just been trained on other instruments. We need to think systematically, considering the integrated workflow, the human AI interactions, and a culture of safety. AI shifts the risk from human misses arising from fatigue or distractibility or availability or a lack of knowledge to AI misses, training biases like we saw with the MRI case, distribution shifts with time, hallucinations, and AI-human interaction misses, where we become over-reliant on AI, for example. What are we doing? The AAPM is doing a lot. MIDRC is a group in association with a number of other organizations, including the NIH, where we're collecting data sets, we're using and establishing ground truth so that we can start evaluating systems. We have committees and subcommittees and task groups and working groups galore. And we had the summit. As I'll show you in a minute, the IAEA has draft guidelines and the ACR is very active. We're also working collaboratively with other organizations. Estro contacted us last night. They're setting up a committee on AI guidance and AI supervision by medical physicists, and they've asked if we're going to participate. So among these things, we have one published task group report, which is sort of inadequate. We have a number of active task groups, but we need more. The good news is TG 455, the last task group to get formed, actually has already written the residency and graduate education programs for AI, and it should be going to review by the new curriculum committee next week. So I said the IAEA has worked. They have published this document, and you can, again, Google search it, or you should read this. It is, if you're writing down notes, PC-9134, the IAEA. This is, I believe, still in preprint form, although it is in the process of being approved. It basically sets up AI like you would set up a LINAC and our interactions with a LINAC. So start by looking at organizational needs, perform market research, pre-select and go to demonstrations, go through the selection and purchasing process, install it, acceptance test it, commission it, evaluate it in the clinical setting, perform ongoing quality assurance, perform clinical evaluations and impacts, eventually decommission it and start the process again with the better, newer AI. There's nothing in that list that you don't know how to do if it was a LINAC or a CT scanner or an MR scanner, right? We can do this. The ACR is taking on a very central role in this. They have download data that you can download. They have use cases where you can actually go in and experiment on an AI system on their computers with admittedly sort of contrived data, but you'll learn how AI works. The second important thing that came out of both the ad hoc report and the summit was virtual clinical trials, not virtual digital trials, by the way. So what is a virtual clinical trial? It is when you conduct a clinical, in this case, what I'm going to talk about imaging trial in silico. So what does that mean? Well, a real trial, you'd have a real population of patients, you would perform real imaging, and you would have radiologists interpret them from the real population of radiologists. Remember that there is a population of radiologists or radiation oncologists as well. A virtual clinical trial, you create a virtual population of cases. The beauty here is you can add virtual tumors and you know exactly who has tumors, how big they are, where they are. You perform virtual imaging on them or virtual treatment, and then you have virtual interpretation. So these are fast and detailed simulations of devices over an ensemble of patients and an ensemble of readers. And that's very important. They're based on anthropomorphic phantoms, and they allow you to do things like develop novel imaging systems, prototype clinical trials, augment clinical trials with simulated data. These are so-called Bayesian trials. Even obtaining regulatory approval. I'm working with a company right now that has an application to the FDA where the bulk of their data for approval of the device is with simulations. And they're not the first. Siemens has done it. Barco has done it. And the idea here is rather than optimize or design a system based upon things like better resolution or better noise, optimize systems to do better detection of cancers, better detection of calcifications, better detection of masses, better detection of architectural distortion. So they offer lots of advantages. They're dependent only on computational costs. They're fast. They don't require you to recruit patients. We can, in my lab, we routinely perform VCTs of 10,000 patients, and it takes on the order of a week. I can do a VCT of 1,000 patients in a day on, a handful of computers with NVIDIA graphics cards. So let me give you an example of a real clinical trial. So this is one involving one of my trials where we were designing an imaging system for breast imaging. We created a pathology simulation and an anatomy simulation. We simulated the deformation of the breast for compression. We simulated image acquisition, and we created databases of phantoms with different types of lesions. The important thing here is you have to calibrate these lesions. They have to be at the limit of detection. If I only use obvious lesions and obvious benigns, every system will just always look perfect. I have to use things at the threshold. And this is why clinical trials, virtual clinical trials, are so efficient, right? When you run a clinical trial, say, imagine a screening mammography trial, and I screen 100,000 women. I'm thinking right now of the TMIS trial, right? 98,000 of those women are normal. 2,000 of them are abnormal. Of the 2,000, maybe 20 or 30 are discriminative to as whether mammography or tomosynthesis is better, right? Because it's only those 30 or so that have some ability to be swayed by the technology. The other ones are so obvious, it doesn't matter what technology I was to use, of those two, at least, right? So I have to spend $150 million to image 100,000 women to find 20 that will tell me whether the device is good or not, right? I can run VCTs and ignore all the rest. I mean, I do have to look at the obvious ones and the benign ones, but it's a much different test. So how did I design my system? We started by trying 8,000 different designs of mammography systems, 8,000 different X-ray tube motions, things like that. We decided on a small subset that we thought that worked. They had motion in the AP direction, from chest wall towards nipple, not just across the breast. And we moved the detector up and down so that we vary the magnification with each cube. Then we had the conundrum. We couldn't actually build a system and test it in patients till we could prove it was safe. So we had to go back and do physics virtual clinical trials where we simulated physics phantoms and imaged those same physics phantoms and showed that, yes, our simulations matched. So it would predict that it should be safe in humans to try imaging them with humans. And so we built the system. And here is the first patient on that system. And I'll just show you some highlights here. That is a calcified fiber adenoma, and it is markedly different than it would look like in a conventional tomosynthesis system. There's another fiber adenoma here that was hidden in the conventional. And if you're familiar with digital tomosynthesis, you know there's sort of an asymmetry in the way lines are reconstructed. Some things in the direction of motion reconstruct better than in the opposite direction. And that's not true in the new system. And we can get right to the edge of the breast. So digital twins, I'm running out of time here. Digital twins were developed in parallel with VCTs. They're digital representations of humans, among other things. And this is really a familiar topic to you guys. They're phantoms, right? And we use phantoms all the time. But phantoms tend to just depict anatomy or some simplified form of anatomy. Think of digital twins as being object-oriented. They have anatomy, they have function, they have complementary information so that they're not necessarily static. And they can encode just about any model, any data set, and do any task that you would think of humans, and many you wouldn't. We could treat people to death in this. We could work out the limits of radiation toxicity with this, things like that, that we can't do otherwise. The number of phantoms that is arisen has gone from, you could count them on one hand in the 1960s, to there's basically an unlimited number today. And the trick today is personalizing them. So creating a phantom from an individual patient, and that is being done routinely. So how realistic do these have to be? This is a very hard question, and there is no single answer. And the answer that we've come up with is unsatisfactory, shall we say. It needs to be realistic enough. So what you tend to do is you tend to reproduce clinical trials that have existed, or a space of clinical trials that have existed. So again, we talked about a cervical brachytherapy this morning. We could look at cervical brachytherapy trials, and then we could start asking new questions. The idea is if you have a space that you have some interest in, so that this is a hyperspace, and these are the data points in that hyperspace that correspond to those clinical trials that Nate talked about in those slides with the black text, right? That's the space of known data. Can I interpolate and ask a question here in the middle of that space? Most likely you can, right? As long as it's relatively smooth space. Can I ask a question out here? Probably not, right? Extrapolation is always problematic, but interpolation normally works. And so this is where the space where you work with virtual clinical trials and digital twins. There are some very cool things that are happening. This is the work of Peter Noel at Penn on something called pixel print, and some of you may be aware of this. He's developed a technique where you can use 3D printers to make human anatomy equivalent CT scans. So the image on that B is a scan of the phantom. That is not a human lung. That is a model of a patient's human lung, right? And then we can take that to different scanners and do different protocols on them. We can embed lesions in them and create libraries of these phantoms, as shown on the other side of the screen. Within radiation oncology, there is substantial work. And I'm going to highlight just one trial in the interest of time. This is a trial done in Texas looking at digital twins and virtual clinical trials in high-grade gliomas. And so there are factors that we can model and there are factors that we can measure. And then you can take a patient and ask questions about their digital twin. What if I had? What if I had treated them this way? What if I had treated them that way? Right? You can't clone patients and treat them 5 different ways and find the best result. But if I have a good model of the treatment and the dynamics of the treatment, then I can ask that question. Right? And getting back to what I said a couple slides ago, it all comes down to calibration. It comes down to how you can calibrate your software with known data so that you can have a realistic expectation that your predictions are correct. And what they showed was that for different instantiations of the same patient, they could achieve different dose savings depending on the response of the tumor and the aggressiveness of the tumor. And finally, to link everything together, Richard Feynman said, that which I cannot create what I do not understand. And so here you can see Mona Lisa speaking to us, presumably in Italian. So there are techniques, including GANs, which would allow us to do basically all of this: simulate patients, simulate the imaging of those patients, and ask clinical questions of it. And so that's one of the good reasons that I'm glad you asked me to speak about all three. In the interest of time, I'm going to skip my last couple slides, and I'm just going to encourage you to come to the AAPM meeting in Vancouver. How many people are planning to come right now? Oh, fantastic. It is looking to be a really good meeting. Registrations are much higher this year than in past years, so we're hoping for an excellent meeting. And if you're interested in the slides I skipped, come see me, because that's my presidential vision for next year. I want to get some feedback. So, lunchtime. Oh, you can do that too.
Right. So, in your opinion, with your opening slides, the Judge Jetson world, doesn't it take a creative physicist to imagine something apart from AI? Like, you have to give it the input. I still think you need the human creativity and thoughts to advance. What do you think about that?
At this point, AI generally has subhuman performance. Humans are more innovative. You just have to look at our history. Look at all the stuff that we've developed. I'll go back to one slide here, motivating this work. Those are innovations. Those are physics-generated innovations over the last century and a bit, right? From the X-ray tube to, the Coolidge tube to proton therapy. Proton therapy was suggested in 1946, right? And we're only doing it today. Cobalt therapy, these things are of human origin. I would hope that we have an enormous role moving forward. That's why I think Kurt is right, that if AI can help us envision things, if AI can make us better, then we should be using it. If it gets to the point where we acquiesce to everything that AI suggests, which there is a very strong risk of that, we're in trouble.
Any other questions? If not, there is barbecue in back along with some salads. Drinks are on the side in the cooler, the cold. And then Rebecca, who's going to be doing a talk later, is going to have a VR demo from